Let's talk about river model, starting by drawing a river. This is our river. We have some discharge to this river, and we want to look at the oxygen profile caused by this discharge. So the river is flowing. We assume it's a plug flow type flow, and we expect there to be an oxygen profile that starts with saturated level here, and then once the discharge comes in and it mixes with the river, there is a drop. We will calculate that, which is easy, but then the challenging part is to predict the profile of the oxygen downstream of this discharge based on standard mass balance analysis. So that's our a task right now. And since we assume it's plug flow, we use the standard equation or general equation for a plug flow situation, dc dt equal to the velocity dc dx plus or minus some reactions. So then we need to look at what are the reactions and what are the reactions. We assume there are a few different terms here that will describe or influence how much oxygen is in the river. The most important maybe, but also the most useful in terms of water treatment in general, is aeration. Because aeration is something we use in bioreactors and in other processes. So we know a bit about how to model aeration. And the standard, or we can call it R aeration, is equal to, and given this old standard for the river model, it's there typically called K2. When we talk about wastewater treatment, we usually talk about KLA. And one of the chapters in the book that you're supposed to read goes in detail into aeration, oxygen or gas transfer between gas and liquid phase. But this then is multiplied by concentration when it's saturated minus the actual concentration. In other words, if we're upstream of this discharge where the river is saturated with oxygen, the aeration rate is 0, because then C is equal to C saturation. So this becomes 0. But as soon as we're downstream of the discharge, we see the concentration is less than saturated. So then this aeration becomes greater than 0, has some value. Specifically in a river, we can look at what influences the coefficient. And if you try to just imagine a river, what would influence how much oxygen comes from the atmosphere into the river?
Temperature. Temperature.
Temperature is one. More?
Chemical.
In the river,
The
waves or the wind power.
Altitude?
yeah, maybe, but some of these things we can kind of summarize into sort of the, you could almost call it surface area. and that is what you will see if you go into the theory. The area between gas and liquid is the main thing, and the area in the river depends, for instance, on how steep it is. If it's steep, there's more waves, so you get more surface of that reason. But you can also see that if you have a really narrow river and deep, it has small surface area to volume, that will give a low value. Or if it's wide, then you have a high value. So these things all influence, and there is a formula that somebody came up with many years ago, where they're saying K2 is equal to dm v, velocity, divided by h to the third, and then we do the square root of that. That's just like an empirical formula that takes all these things into account. So height or depth, kind of a diameter, and the velocity. All this adds up, and that's just, turns out to work okay, so it's being used. It's not so important. The important thing is we have a value that is typical for some river, or in other cases when we aerate something, we do something else. And there are also examples from practical life where people put in extra barriers to create more turbulence and more mixing if a river has trouble staying nice and aerobic, because we don't want it to go too low so that fish is dying. That's kind of the main idea here. Keep it always from going anaerobic for sure, but even not close to that. All right, good. The dm is the molecular diffusion, and that's where the temperature effect comes in. But good enough. That's good enough for now. Then we have, that's a source of oxygen. Any other sources of oxygen? So we can say that's number one.
Photosynthesis.
Okay, number two is photosynthesis. And there, we have some variation over the day from, if you have rate P, we can say it's only going on when the sun is up. So we have significant aeration in the middle of the day due to photosynthesis, or we can have if there's much algal activity. What we will see though when we go through this is that this may not play a very big role, because typically the critical situation is when it's dark, when this is not on. So therefore we don't need to put too much effort into that. As you can see in the notes, there is a formula and stuff, but let's not worry about that now. Let's just move on to a third process. And now we're looking for processes that has the opposite effect, that consumes oxygen, because these are really the only ones that supply oxygen. What will consume oxygen? Microorganisms doing what?
Eating the organics.
Right. Eating the organics that come in the discharge. So we can talk about, for simplicity, BOD, biochemical oxygen demand. So let's just call that R BOD. And that's the one thing that is of particular interest that we can do something about how well we treat the wastewater before it's discharged. So that's typically why this analysis is done, is to find out how much treatment do we need to avoid low oxygen downstream of the discharge. There are kind of two versions of this, there is an added one, extra one, which we can call Rn, which has to do, it's also a type of a BOD, but it's the BOD related to nitrogen oxidation. In other words, if we have ammonia, which often is the case when we have BOD, we also have ammonia. And that, if you have microorganisms consuming ammonia, they will also consume oxygen to make NO3. To keep it very simple, we'll have more details on this next week when we talk about nitrification. But roughly speaking, that's the BOD demand related to nitrogen. So that, in some cases, we need to account for that, in other cases, not. By the way, this BOD, the whole term, the whole analysis came from analysis probably 150 years ago in London, looking at the Thames River and looking at how oxygen, I mean, London was really stinking because it went anaerobic. So then they started analyzing and they developed this method called BOD. And that's kind of still what we're doing, more sophisticated, but here we kind of see where it comes from, this type of river analysis. And then we have a fourth process, also consuming oxygen, which is what we can call rate of respiration. And that is mainly what we have. The photosynthetic organisms, they produce oxygen during the day, but during the night they consume oxygen, just kind of to maintain their activity, maybe to build new things from what they generated with the solar energy they got during the day, they consume. So in the middle of the night, even though, so you can look at algal activity as a nice contribution to oxygen, but the more algal activity you have, the more trouble you have in these kinds of cases, because during the night they consume oxygen. Right, so those are the processes we need to account for. So that means we can take our general equation now and turn it into, or put terms into the reaction rate. So we have Vc dt equal to minus Vt Cdx plus our aeration plus our photosynthesis minus our BOD minus our respiration. And then, as we always do when we have mass balances, we try to simplify. So what is the first simplification we usually do? Steady state. So we assume 0. We also often do a few other things, but for the sake of our discussion and to make good progress, let's also assume that the algal production of oxygen is not very interesting for us. We don't have much algal growth there. It's a purely BOD discharge. So let's assume both of these are 0. And in addition, we define a new parameter which we call oxygen deficiency. equal to m, which is Cs minus C. If we do these simplifications, we see that the whole equation changes quite a bit. dc dx v is equal to just K2 times m. Notice m is aeration, we replace by K2 times m. And but we also need to keep our consumption, which is RBOD. There is another trick that these guys who developed this made. They said, well, we have the x here, that's the flow direction, but we can define a new time. What we can say is flow time. This t, flow time, is equal to x divided by v. It just simplifies, since this is all manual. We could do it, of course, today on the computer, but when they developed this, it was all manual. So if we do that and we integrate, we end up with a pretty messy equation, but it can also be expressed in a very simple way as dm dt is equal to K1L minus K2M. And I guess I forgot to say this is rate of BOD is often modeled just as a coefficient times the BOD in the water. So L is an expression for the measure of BOD. And BOD is just similar to the COD that we've been working on in our biogas model. You see in the notes some of the details going from the general equation over to this, which is named after the guys who developed it, which is Streeter-Phelps Equation. If we take this now and put it back into our drawing of the river, and we put these new parameters in there, then we see that this new m that we defined, m is equal to Cs minus C. So that's M. So M is what we're looking for. It's the deficiency of oxygen, the lack of oxygen compared to the natural state of saturation. That was wrong. It should be there, up to saturation like that. And then we can also define the largest M is what we can call M critical. And when does that happen? Since we have now changed the axis from being x to being t. So this happens at t critical. Then we just defined a couple of new conditions or parameters that describe how bad or good the river is doing. If we then also include here that this initial drop we can call M0. Because remember, when we do integration, we cannot do an integration here because this we consider to be an abrupt change. So our integration with this differential equation starts there. So M0 is the start value, initial condition, and then we can simulate this by the equation for M. So we have now defined a few, or the critical situation. So then we want to find out how do we calculate this critical situation. Where does it occur? And what is the concentration of oxygen there? So any ideas how we could approach finding that spot? If we look at now the equation we have, the Streeter-Phelps equation, changes in oxygen deficit with time as a function of the consumption and the supply of oxygen. So how do we, what's our next step if we want to find this critical? Well, then we look at what do we know about this equation when this occurs?
It's 0.
It's 0, because we see that the change in m with distance, which we now have called time of flow, it's 0 right there. So in other words, that's a nice little trick. We just say that equation is equal to 0. So we say K1 L is equal to aeration coefficient times m at that point. So then we can solve it. But before we go that far, we should look at how is L? L is the BOD. And the BOD, of course, is the stuff that we add here as discharge, but it is broken down as we go. The reason why oxygen is consumed, it's consumed for the microorganisms to break down L. So in other words, L is changing with distance, called time in our equation. That is typically expressed, and this you can read about in the book about BOD, is L is equal to L0 e to the minus K1T. That's how BOD is disappearing gradually. It's the equation you come up with if you just look at what's happening in your BOD test over time. So what is the BOD test? Just to take a step back. The BOD test is where you take your discharge, you put it in a bottle, and you look at how oxygen is disappearing with time. And if you do that, it's a batch test, so it's kind of like studying. You take a sample and you see what's happening as this bottle is flowing down, kind of. So a batch test is kind of like a simulation of what's happening here in the traditional batch test without aeration. So what they had to do, they would have to have many bottles with different dilutions and follow them over time. Typically, the standard method was 5 days. So they just put all these bottles, let them sit there for 5 days, and after 5 days, they measure how much oxygen is left. And the bottles with lots of wastewater, they would become anaerobic. Those with very little wastewater had very little oxygen disappearing, so the most interesting ones were the ones that had removed quite a bit of the oxygen. This was not very efficient. So the modern BOD test, you actually have a process that adds oxygen to the bottle as the test goes on. And then you record and you can see it on the screen, how much oxygen is used. So the modern BOD test is almost like a direct simulation of what happens in the river. Except you have a constant KLA that is set by the apparatus. By the way, supposedly, the reason why the 5-day BOD is still standard, it's because typically the Thames River takes 5 days from the city to the sea. So, some old ideas, history can still remain after 150 years as the standard. So many discharge limits are still given by BOD 5 values. But anyway, this is how we do it, and if we take this then, we have K1L equal to K2M, or it's in other words equal to K1 L0 e to the minus K1 T. If we solve for this M, or this case, we find M equal to K1 divided by K2 L0 to e to the minus K1 T critical. And of course, then we have to find T critical, and again, just moving the equations around, T critical, when the oxygen level is the lowest, is equal to 1 over K2 minus K1 ln K2 over K1 multiplied by 1 minus M0. Okay, I gotta keep this straight now. Times K2 minus K1 divided by K1 L0. So here we have the equation for T critical, and this is then M critical. That's how it's done. But of course, you could do it probably easier. Just making a model in the computer. And if you notice, Aquasim even has something called a river compartment. So instead of using the CSDR compartment that we always use, you could use the river compartment and do this type of simulation. But this is the basics of the Streeter-Phelps analysis of oxygen depletion or deficiency in the river caused by a sewage discharge. And then we can say that, now let's say that this M critical we calculate by this method shows that now this is not within the requirement of the government. You need to cut that in half. Then we can try to find out what should M0, now M0 is not one that, well, we could modify that a little bit, but it's not the most important. The important one is the initial BOD at the discharge. So this is essentially where L0 is. After it's mixed here, we find L0. Okay, that's the theory. I'll stop there for if there are any questions.